strong equilibrium, say, what's that? That's strategy profile, that's what?
It was where no coalition of players would deviate.
And when a coalition would deviate, then what would be the rule for coalition?
That there is no coalition where the profit of the utility is better than the equilibrium.
For each member of the
Yeah.
coalition. Okay, so we say that a coalition has a profitable rule if there is a coalitional strategy where each member of that coalition strictly improves his utility. All right, there is and then a strategy profile, of course, that does not possess any improving coalitional deviations would be a strong group. There is a stronger notion than that would consider deviations, coalitional deviations, where each member of the coalition does not harm his utility, and there is at least one of them who strictly increases his utility. Why would that make sense? How would you justify such a deviation for a coalition? Why would people join the coalition if their utility does not change? Well, okay, strictly speaking, if we follow the protocol of normal form games where utility are not transferable, there is no incentive for individual players to do that. On the other hand, if we already talk about coalitional deviations and some agreements between the agents to make a deviation, then there is, something there in the air saying that, okay, then if there is at least one, if there is a coalitional gain, they probably can share that. Okay, but that's not in the model of non-cooperative games. It's just the intuition why such a deviation may probably happen. And then a strategy profile that is immune to such coalitional deviation would be called, strict strong equilibrium, because that notion of stability is stronger than a strong equilibrium, right? We allow weaker deviations of coalition, so there will be more deviations. And that's why to be immune to more deviations, meaning that the concept, the solution concept itself is strong. But okay, focus on strong equilibrium, that would be enough. And then we briefly mentioned, for instance, the example of prisoner's dilemma, where we have a unique Nash equilibrium, and we saw that Nash equilibrium is not a strong equilibrium because both players may deviate to both denying the crime they've done, and then both of them will increase their utility. Now that new profile also is not a strong equilibrium. Why? Because it's not even a Nash equilibrium. From that profile we have unilateral deviations by individual edges, right? So there's no strong equilibrium in that case. Which is not surprising at all, because we know there are games without Nash equilibrium at all. So of course, strong equilibrium is even a more rare thing to have. But there are games where strong equilibrium do exist, and one of them, we said it's resource selection games. With monotone, let's say, particular. In fact, that's true for all monotone games, but we will show it for games with non-increasing. And that's even for the normal time. And for that, for those games, not just that strong equilibrium exists, it's more than that. In fact, every Nash equilibrium of such a game, let's call that the set of all Nash equilibria, this set of all. So every Nash is strong. So by definition, we know that every strong equilibrium is, of course, a Nash equilibrium. Because in particular, that profile is immunity deviations by signal coalitions. Right? The other direction we have to show. So let's see why that's true indeed. So we need to show this direction, right? We have to show that every Nash equilibrium is a strong equilibrium that way. And then we will do that. So let us have some profile which is a Nash equilibrium. Assumed by the contrary, it is not strong equilibrium. What does that mean? It is not a strong equilibrium, so there exists a coalition of layers, and the coalitional strategy, let's call it S prime C of those coalitions, so that the combination of the strategy sets for all the members of the coalition, so that every member of the coalition we have that his utility from plane S prime C S minus C is greater than the utility from plane from S. But let's look at all at those two profiles. The one before and the one after the deviation. What I want to claim now is that the congestion vector of this profile is the same as the congestion vector of this profile. And to show this thing, we use strongly the fact that the games that we have are resource selection, so every agent uses exactly one resource. So if you look at the total congestion on the resources, what is it? Under profile S, or in fact under so this is how many agents we have on each resource R. We sum up over all the resources. What's the sum of that? Each agent now uses exactly one resource. So what's the total congestion? N. Yeah, exactly the number of agents. Right? In cases where an agent may use several resources, that wouldn't be true. For resource selection games, it is true. So the total congestion is the same. But I want to say that on every resource we have exactly the same congestion. Why would that be true? So if the total congestion is the same, and the individual congestions on resources is not the same, then if we have smaller number of users in some resource, here there will be another resource where we have larger number of users, right? So there would be, so if here we have different congestion than in S, then that there would exist resource R so that the congestion on R in the new profile is greater or equal than the previous congestion plus 1. If there was a change, then because the total sum is the same, then at least in one place the changes out. What does that mean? Now we have more users. Who are those users? Okay, some of them do not belong to coalition C. Okay, so we do not require anything from them. The utility can deteriorate, that's all right. But since there is someone new here, there must be at least one agent who does belong to the coalition C. He is the guest on that resource, right? So there is some agent I, so that his strategy, his new strategy is R, and it's different from his old strategy. Right? The strategy now is actually one resource. But now the congestion on that resource is higher, meaning the utility from using that resource is lower. So does our agent gain anything? No, he actually loses something. Right? So the utility of I from this thing is actually lower than his old utility. So indeed we have this. That's not the end yet. But now actually we use the same logic as here. So now we know that the congestion on all the resources is the same. So the only change that the members of the coalition C could make, they would just, there would be just some permutations, they would exchange resources. Right? Because the congestion on each one of the resources stays the same. So if they exchange resources, can it be that all of them gain from doing so? No. Unless they had player-specific utilities, which are not part of the model. So every user of a given resource gains exactly the same amount given the same congestion. So if we just exchange the resources, if I gain, you don't. And say the change in the strategy is say it's possible for all the agents to alright. So that's that. Congestion gains in general, no stroke equilibrium in general, but always, as we remember, the strategy acting stronger than that potential. One more important thing about congestion gains in particular in the application to networks. So assume we have a network approach, a very simple one. We have two cities A and B. and there are two paths that go from A to B, one through C to C, another one through C to D. So there's one path, there's another path. Now every user of each of those edges gets constant cost on those, on CB and AD. So whoever uses that link pays 1, and agents, every user of this link would pay half plus x divided by 200, where x is the number of users. And here, same function, but I will just denote the number of users as y. Okay, so now what we want to do is find equilibrium values for x and y. I have to tell you how many agents we have in total. In total, we have 100 of troubles. So intuitively, what would you guess? No.
50-50.
Half on the upper link, half on the lower link. That is correct. And the intuition is, well, in fact, you know, the costs are symmetric, so we probably should expect symmetric equilibrium here. Let's indeed check that, first of all, that is an equilibrium. And second, in fact, that will be the only equilibrium after permutation of the agents, right? So choose the numbers of x and y. So why is that an equilibrium? So take someone who is taking the upper link. Say how much, so we said x equals y equals 50. Right? Say how much does it pay now? Half plus what? A quarter, right? Plus 1. So that's 175. Okay. Now, if he changes his strategy, there is only one possible change. He goes down. He would pay 0.5 plus something greater than that. It will be 101 divided by 200. Great. Yeah. Sorry, yeah, 51. But that's greater than quarter plus 1, so that's more than 175. No incentive to do that. Okay. Say, indeed, x, y equal 50 is a Nash equilibrium. Now, why we cannot have any other equilibrium where, let's say, x is greater than y, or the other way around? The same very reason. Right? If, so here we will have y divided by 200, here we will have x divided by 200. Right? If y is strictly smaller than x, then this will be less or equal than x divided by 200. Okay, so in fact, yeah, 49 and 51 is also fine. There are, like, when you add one, you will get. Oh, well, in fact, so since we have the that is why is that? Because if we have an odd number of on one side, we will have an odd number on the other side because the sum is given. So that's actually impossible that if I move from one side to another, I will get exactly the same number as it was because I changed the parity. Right, so it's actually impossible to have equality here, so it will be strictly less than that. So I do not indeed have, even if we are close to the half, but not exactly half, I will never have, I will have an incentive to deviate to the other half. Right. So indeed that is an equilibrium, and that's the unique equilibrium. Once again, after permutation of the planes. Now let me show you some magic, although quite an unfortunate magic. So assume that the city council builds a new road, and that road is free from C to D. The cost there is 0. Isn't that a good thing? Everyone will say yes. Yeah. Well, what happens? So now we presented a new path from A to B, right? Through A, C, D, B. And now an interesting thing happens. Now the only equilibrium that we will have is for all the agents to take this new path. And then the cost will be what? Twice 0.5 plus 0.5, 2. And what did we have before? This. So the cost for each user has grown. That thing. Why is that the only equilibrium? Indeed, look. So let's again show that this is an equilibrium. Say now I'm taking this path, this is what I'm paying. If I change, where can I change? Either to the upper link or to the bottom link, how much will I pay? So I stay on the same link that I used before, and then instead of paying another part of that, I will pay 1. Right, so it will be it will be actually the same, so I don't gain anything. So that's indeed an equilibrium. Why we will not have other equilibria? Because there always will be incentive for the agents to join this path. Because if we have someone who uses either that link or that link, right, that would mean that either there or there will be less than all the agents. And so instead of paying 1, the second part of the path, I will be able to pay something which will be less than 1, because this part will be less than half. Right, so I would replace the constant cost of 1 on the second part of the path with the congestion-dependent part, which will give me the half of my cost less than 1. So there will be an incentive to deviate. So not that we just introduced a new equilibrium, which is bad, it's also the only equilibrium. This paradox is called the Brias paradox, by the name of the guy who found that interesting phenomenon. And there is lots of work on how to avoid those things in the network so that they would introduce the high cost for the agents. Any questions here? The last funny bit that I'm sure you will enjoy in projection games is to look at much an exercise, so it's not something to remember, that's something to train yourself to operate with. We now will have an extended model of congestion games, which is called a weighted congestion game. The difference is that now every agent has a given weight, okay, which is constant, and when an agent joins the research, he brings instead of congestion 1, as in the last model, this amount of congestion. Right, so every agent has weight, say, WI, which now the model is more general than classic congestion games, and in fact in those congestion games we may not have an actual impure strategy. And what we want to do now is to find an example that would show that. And we want to find a simple example where we would have 2 players, 1 and 2, and there will be 3 resources, A, B, and C. So we want to construct an example where there will be no Nash equilibrium, and there is a hint, and the hint is, let's define not symmetric strategy sets, because this is where the non-existence will lie. And for the first player, we will have the set that includes strategy A, the single resource A, or the pair B and C. And for the second player, we will have either a single resource B or a pair A. Okay, so now we have 2 players, 2 strategies for each one of the players. So I actually can draw the pair of matrix. I wanted to make too big. So we will have the first agent here. Here are the strategies. And we will have the second agent here. And here are. Now, to complete the example, I have to define the cost functions. Right? I have to complete the definition of the game. Say, I have to define the cost from using each resource at all possible congestion. So there will be CA in congestion 1, CB at congestion 1, CC at congestion 1. Same with the higher congestion 2. And finally 3. We can't have higher congestion on the resource, we only have 2. Oh, I didn't give you the weights. Say, yeah, the weights are as their indices. The first agent is of weight 1, and the second agent is of weight 2. That's why we may have congestion of 3 if both agents use the resource. did try to guess those things. So what would you, that's your examination, you have to solve that. How would you think? Well, what do we have here? In the pair matrix, we have pairs of the agents, right? We can actually write them down using those symbols for the costs, right? So we know how the expression looks like. Then what else do we know? We know that there should be no Nash equilibrium in that game. That is, we must have, in fact, a cycle in this matrix A. This is not an equilibrium, so either this agent has a deviation or this agent has a deviation. Well, take some direction. Okay. This also should not be a Nash equilibrium. Now we know that the first agent will not have a deviation back from this cell. Say the second agent will move, and so on and so on. And now we have what? A set of inequalities on the costs that use that, and from that we can figure out the values of those costs. You had a comment? Yeah.
Just should we guess or should we?
Well, if you have a good guess, we can go ahead with that. I actually, to guess those things, I had to write down all the inequalities and then also try to find a sequence so that all of them satisfy that. That's quite an exercise to do, right? But I'm not saying that this is something you should be able to solve in 5 minutes when you, for the first time, see that, okay? But you have to know how to approach such a problem. And the approach is actually direct, right? Just write down the form of the utility function, write down the inequalities that would say that this utility function does not correspond to Nash equilibrium. That's it. Okay? And then, yeah, the guessing point is a bit of guessing, but that's an intelligent guess. Okay? You have lots of help there. Okay, so how do the utilities look like? First agent, second agent. Okay? So if both of them use, if one uses A, the other one uses B, yeah.
CA1.
CA1 for the first agent, he is alone on resource A, his weight is 1, so the congestion is 1. Now this guy is alone on B, so he only pays CB, but his weight is 2, so the congestion is 2. Here we have both of them on B, and the first one also uses C. So he pays for B at congestion 3, because now the 2 of them are there, and he pays for C at congestion 1, because he's a light, is the light agent. The second one still uses B, but now together with the first one, so he pays CB all 3. And so on. Here we have BC and AC, both of them are on C, and then they also, this one uses B and that one uses A. So there will be CB1 plus CC3, right? And for that one, there will be CA2 plus CC3, correct? And finally, this one uses 2 resources. He has another one on resource A now, so there will be CA3 plus CC2, because he's a heavy one. And here we have CA3, and that's it. And now I want CA of 1 to be strictly greater than CB3 plus C C of 1. That means that the first agent has a deviation from here to here. Now from this profile to that profile, the second agent deviates. So we have that CB of 3 is greater than CA of 2 plus C of 3. And so on. This must be greater than that. CB of 1 plus CC of 3 greater than CA of 3. And this is greater than that. CA 3 plus CC 2 greater than CB. Now, we also use the monotonicity of the cost function, try to arrange those inequalities in a chain. Okay. I will not do that now. I'll give you a final answer, and I'll let you to play with it at home. And this is, for instance, that solves that. Let them have zeros when the congestion is 1 on all the resources. At congestion 2, let A cost 3, B 4, and C still 0. And at congestion 3, make this constant 3, 4, and this grow to 2. This will bring this thing to 0, this thing to 4, this will be 4, this will be 4 as well, 2, 5, 3, and 3. Grows, 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 grows. No measure. Shall we have a break now? And then there was the last thing about congestion games. Unless you have questions about congestion games, we'll move on to something else after the break now.
Do you know how this comes? Anyways, she said she doesn't know the equivalent because it's like this. So you build just like it's not capable by something. Before we go to that part, I want to know why is C and why C. I got it. One player weight is 1 and 2 is 3, right? So here, player 1 is strategy 1, so it's CV1. And strategy 2 uses strategy B. Yeah, because of weight, right? Yes, because of this. Yeah, so it's CA1, CB2. Yeah. And here, the player one use B and C. Yeah. And 2 use B. But in here, they all use B. they all use the B. So it's not the B1 or B2, it's B3.
So it means because player 1 is play wet 1 and player 2 wet 2, so they have B here, so it means C.
They all use it. They all use this.
So it's CB3.
So it's CB3, and the one player 1 uses CB0, so it's CB3 plus CC1. But in here, two only use B, so it's CB3. It's not CB2 because they all use B.
Yeah.
So it's 3. So yes,
Because in this box they have 1C, so here is CC1.
But in here they all use B, so they can only use CB3.
Okay.
It makes sense.
Yeah.
And in here as well.
B1.
那这条有这些0.5加上250，0.5加250，那总的有这是2条加起来，然后它会比原来的大。为什么？0.5加0.25加0.5加他算错了，我会算错了，这个我会调整。他原来意思是这两个加起来的东西，应该会比原来的大，因为所有人都会去选择，这个就是加分条件有趣的地方。
反而比原来高了，但他们却都用这条。
对，全部都有这条线，不会去用因为你要想这条加起来，这条的值，你就是0.5半嘛，我算一半，肯定0.5加正一半，肯定是比这个小的，所以你花费就小了，对，你会觉得怎么会啊？这个是 cost 呀，这个是 cost，那这个 cost 太小了，这个是0.5加上0.25，这个0.5加0.25。
0.7嘛，0.75比这小。
0.9比这小，对 cost 小。
不是这两个0.7，为啥是它1.5啊？
那你就知道了。
你这样就是1.75了。
那有不会这样讲？不是我们在算它是干啥？当然选正常，因为这条 cost 少，所有人都会选这个，这就是那个就发给这个有值的这样。对啊，他就是为了表达这个意思啊。
那不他就有些还是比原来低啊，
但是就是他有那水平的人，所以他会选这条的，他就是说这个加上小数这个，只要加了这条，所有人都会去选这个。可能我说这就是这个是说这个。那我觉得对我是这个，他就发现即使稍微的不同，比如第二个方程为什么是CB3加上CC1啊？
这个不用 C 吧？这个和这个两个人都用是吧？是吧？最后3，他根本就没有位置3的东西，他只有位置1和位置2。
我懂了。
位置3是属于比较
懂了，我就想说这是2，为什么变成3了？因为
对啊，他俩都很低。
这个他就是为了表示这个意思。
关键是，如果按你这样说的话，
就是说他的意思是，如果是这样的话，你找到确实是这个值嘛。但是如果你加了这条线，它也可以就变了，会变成这条东西。它为了表达这个，但是关键是
这个那是真的有可能，你知道吗？
对啊，
它就不是固定的，它这个范围。因为就算这是0.5，这是
这就不是你想所有的东西都对不起一半。 200%，所有的玩家都选这条路，那应该这个就是1吧？为什么这是1呢？所有的玩家都选这条路 ，X 是选这条路的玩家嘛 ，Post 选，那这里就是0.5加上200%100，所以是0.5加0.5嘛，0.5加0.5嘛，然后乘以2嘛，然后那就是那个了嘛，对吧？因为它有个条件，你超方 x 加5.100，对 x 是100啊，对吧 ？x 可是没有100啊。你是说在这条路上，在这条路上，在这条路上，正常的话是这里选一半，这里选一半，对吧？对吧？是正常的话，这里走一半，这里走不行。对。这条路的话，是因为这条路所有人都走上面，那就变成100了嘛。所有的人对，然后所有人都是走上面，然后好奇怪，这个东西是等于2。对 ，cos 是1.5，对，我忘了。就它这边是分开了2条路，对，因为它是为了找到时间的，是2条，对，现在的话是只要接到这条路，对，好奇怪，对，因为你看，它这边不再是分成2边了，这条路就只有1条路，所以100人都走这条路，这条路的 cos 是200%，1.5就是1.1加1.2，所以是这样，对，就是这个嘛，所以说是0.5，对，懂我的意思了。这样子的话，这样线反而不好。
Why she say that it's not equilibrium? I just think another way. If we do in the matrix, if we use a best guess point, we found one equilibrium. Yeah, I think you just try to find the best guess point. You will see here. 3 is best guess point.
It's no stroke.
Yeah, I don't know.
That one.
Yeah.
And in here, I will choose that one.
Yeah, here.
In here, I will choose our one. In here, I will choose this one. It's not 0, it's 0, 4.
Oh, 0, 4, okay.
Yeah, 0, 4, so I will choose this.
Okay.
Yeah, so you got the deviation in strategy. It's a circle. It's a circle, so you got no dash equilibrium.
Oh, okay. I'm sorry, I'm wrong. Oh, yeah. Hmm? Right. Here. Huh?
No,
What's it like?
it's 3, it's not 5.
Fuck.
Yeah,
Yeah, okay.
here.
Yeah, okay. Okay, I got it. So it means we still use the spawn. But I want to know why she compare this and then this and then this and then this.
Huh?
In the first here, then she used only agent 1 to compare, and the second one she used agent 2 to compare.
That one?
Yeah.
Yeah.
And then they use agent 1 again, and then she used agent 2 again. Why we don't use both?
Because if you want to compare the other one, this
Okay.
yeah, it's how to calculate the Nash image.
Okay, I got it.
Oh, I got a question. This one and this, 0.5 at x divided by this is the cost or
Before that, I get confused as well. Why we have to term with 2?
this is the cost or utility?
Cost.
Cost.
Yeah, it's cost. But I think this has get a little bit confused. She say in the first part, she say 2 term with 0.5 plus 0.5, right? But what about this?
Because in this situation, because people will choose this way. Right?
Yeah.
People all choose this one. Because when you start here, you can see this cost is 1, this cost is -1, so you always choose this one, and you will face 2 options. One is 1, one is 0, so you will always choose 0, and that you only have one way to go.
No.
It means
So
in
everybody.
this situation, it's compare this way and this way.
Yeah.
It's not only about compare this way.
Yeah, I know.
But this way is still less than.
Yeah, still less than 1.
Yes.
Oh.
But in here, it's not x and it's not only y.
So
y,
everyone will choose
x
this one.
plus
So,
y.
so
X plus y is 100. It's not 50. So it's 100, so they are equal.
Oh.
But people will all choose this way. If one of them didn't choose it, it will less than. So it's always a Nash
So it means this